You are just invaluable. Not just because of that, but lots of reasons.
Thanks, Dr. T.
You're welcome, sir. Thank you. I owe you a great favor. All right, just closing your eyes and sitting up straight. Let's get your back a little bit straight. That helps kindle your awareness. Just let your breath unfold. And on one of your hands, just bring your forefinger and your thumb together. Either hand is fine. And just bring your awareness to that point of contact. What does it feel like where they're touching? Really get in there. The more you notice this, the more vibrant it becomes. Could you figure out the edge of that sensation? How big is it? What is the texture of that sensation? Does it feel constant? Does it feel dynamic? And just release those fingers, that thumb, finger and thumb. When you're ready, come on back, gently opening eyes. I have a story to tell you. I have a really good story to tell you today. It's a great story. So, anybody know who Zeno is? Who's Zeno, Luke?
The guy who solved the turtle paradox thing.
Sounds about right. Yeah, what do you know what that paradox is?
It's like the turtle, is at the start of a track, and to get to the finish line, he has to go halfway. To get halfway, he has to go halfway. To go halfway, he has to go halfway to the halfway.
Beautiful. That's beautiful. Yeah, that's exactly it. So the whole the Greeks were really, some of the Greeks, especially Zeno, was really intrigued by infinite progressions. And I don't know if I would say Zeno solved it necessarily, but definitely posed
A
it to
weird
us.
solution.
Yeah, we're gonna solve it. We're gonna solve it. I think, because Zeno's argument was that you can't get anywhere, right? So Zeno was arguing that,
Ever.
what?
Ever.
Ever.
Can't get
That
anywhere.
to get from here to the wall, I've got this distance to travel, let's call it one unit of me to the wall. I first have to travel half that distance, and I still have to travel half the remaining distance, and I always have to travel half of what's left. So there's always something to travel if we think of it this way. So Zeno argued, you never get anywhere. Motion is impossible, really, traveling from one place to the other, and we know that that's not true because we travel places. Part of the thing that Zeno was thinking of wrong is that each of these things took the same amount of time, so that's kind of one of the flaws in that. But the problem came down to this. Oh, by the way, all about today's story and more stories to come. So Zeno was saying, okay, look, to travel that distance, one full distance, I still have to travel half the distance, and then I have to travel half of that, so there's a quarter left, and then I have to travel half that remaining distance, right? So to travel from here to here, I first have to travel half, and then I have to travel a quarter, so that's plus another quarter, and then traveling half of that, that's plus an 8, plus a 16, etc. So it's this infinite sum. I'm going to keep an eye on you today. It's this infinite sum, and so Zeno's argument was, well, that never ends. Not a bad argument. We can see what he was getting at. Let's think about this argument a little more abstractly. So this is Zeno's full progression. If we just assumed that things could go on forever and ever, it would look like this. But what would it look like after I do this just n times? So after 3 times of doing this, it would look like this, right? So this would be n equals 3 times. And then after 4 times, it would look like this. So let's see if we can kind of generalize this. So after n steps, how far have we traveled? Oh, you weren't. I thought you were asking a question, Fernando. No, just doing some other stuff. That's cool. So that would look like this: a half plus a half of a half plus a half of a half of a half, and then this is 1, 2, 3, and then we go out to n steps. So it would be 1/2, and I'm going to try to just start generalizing that right now. 1/2 times itself n times. And so this whole series would look like this. Our sequence, 2 squared, 1 over 2 cubed, plus 1 over 2 to the n. It would be nice to be able to just have a nice, lovely formula to add that all up. Wouldn't it just like, so I can look at it and go, oh, it's this. No matter what n is, I've got this function of n that tells me exactly what that sum is. So that's what I want to first derive for us today. This is called a geometric series. And we've been talking about, so contrast that to the word sequence. The word sequence is a list. So sequence equals a list. A series is a sum. Just want to make that correlation right now. Anytime you see series, it means sum. The geometric part means that the common ratio between these things that are called terms of the sequence, those are the things I'm adding. The common ratio, or the ratio between subsequent terms is a constant. So it's always a half. I'm always multiplying by a half to get the next term. That defines a geometric series where a constant ratio is applied. So in general, a geometric series looks like this. A finite, let's start off with finite, geometric series looks like I've got some number that I start with. And then I multiply that by a fixed constant. We're going to call that r for ratio. So plus a times r. And notice that I just did a times r to get there. And I'm going to keep doing that. So the next one would be plus ar squared. Again, I just multiplied the previous term by r. And I keep doing that all the way out to, if I do this n times, so this is 1 time, this is 2 times. If I have n terms in here, so let me try to lead up with a better way of saying this. When I had 2 terms, the power of r was 1 that I ended with. When I had 3 terms, I ended with a squared term. So if I want to have n terms here, then what is going to be my power of r that I end with?
N minus one.
M minus 1, right? So when there was 2 terms, we ended with a first. When there was 3 terms, we ended with a squared. It was just a little bit less, and that's because we're starting with r to the 0. So just, there's ways to think of it so that it could be n too, to discounting it a very particular way. So there's going to be n terms here. Let's actually write that, n terms. Let's call that S sub n, sum of n things. Everybody with me so far? Is this looking good? All right, now we're gonna do some really cool magic. And we're gonna come up with our formula for that general finite sum. I'm gonna multiply this whole thing by r. So I'm just gonna multiply both sides of this by r. Again, r is a fixed constant. And so this side becomes r s sub n, but the right side becomes, now watch this how I write this, you're gonna wanna do this in your notes. This becomes a times r, and I'm just gonna write it under that one. And then this becomes a times r squared. When I multiply this by r, I get that. When I multiply this by r, I get ar cubed. And I keep going, and eventually I'll hit ar to the n minus 1. When I take this term right in front of this one, and I multiply it by r, I get this one. Look at the rhythm. Or something. Yeah, something like that. Yes, I got them all kind of skewed now. And then what is my very last term going to be? What do I get when I multiply this by r? Ar what? N, right? Because it's just r to the n minus 1 times r to the first, add the exponents and you get that. Just look good. All right, now something a little bit unexpected. I'm going to subtract down. So I'm going to subtract over here, and I get s sub n minus r s sub n equals, look at what beautiful stuff is happening on the right. This is just a minus 0, so that's a. This is going to cancel, 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 all the way down. Now there's nothing to cancel this one out. So I'm left with minus a times r to the n. Now this left side, I can factor s sub n out. So I could make it 1 minus r times s sub n. And over here, I can factor an a out. So I'm just doing a little factoring on each side. What I wanted was a formula for s sub n. So all I have to do is divide by this number here, provided this number isn't what? What don't you want to divide by ever in math?
0.
0. So what should I say r is not equal to?
1.
R can't be 1. So if r is not equal to 1, divide each side by 1 minus r. And what we get then is our beautiful formula. S sub n, and that n, I really like that n. That's a nice n, is going to equal a times 1 minus r to the n over 1 minus r. This, my friends, is the sum of a finite geometric series of that form. So let's actually summarize. This is the sum of the first n terms, sum of, let's just write this out, a plus ar plus ar squared plus ar n minus 1. I'd like to note something else too. This a is the first term in that sum. So just put a little note. A equals the first term. That's really important, very helpful for us. So you could think of this formula as, let's write it out in kind of a heuristic way. So this is first term times 1 minus the common ratio to the nth power over 1 minus the common ratio. Now I hope in my heart of hearts that you would never cancel these things in any weird way. Please just make a promise to me in yourself, like a quiet promise, I will never cancel these things. Because they don't cancel. That's why we got this formula perfectly like that. I could see weird things happening, and I'm trying to stop that before it happens. Because I've seen some weird shit go down. I've seen weird math stuff go down you wouldn't even imagine. And that's one of the things I've seen, people doing that. So here's our beautiful formula. Now we can answer Zeno's question. Oh wait, not yet. Not yet. So this is for our finite sum. This is the sum of this thing right here. So that's definitely of great import to us. Wow, I've never said great import. Sounds like I should have like a captain's hat on or something like that. Now I'm getting worked up. What we would like is a formula for Zeno's problem in infinite geometric series. So an infinite geometric series looks like this. First term, multiply by r, add that on, multiply by r, add that on, and keep doing that forever. So we put some ellipses here, ellipses, to indicate that goes on forever. Look at what we have the formula for. So to find a formula for this, we let n go to infinity in our finite series formula. So let's kind of write out what's going on. So the finite version looks like this: a plus ar plus dot 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 plus ar to the n minus 1, and that is equal to first term 1 minus r to the n over 1 minus r. So we're going to let n go to infinity in each side of this thing. If n goes to infinity over here, there's no math to do, there's just erasing the end. So this becomes a plus ar squared. That becomes an infinite sum. The right side is where the action's going on. And I think I gave this result the other day. If we had limit as n went to infinity of a power, a fixed base to a power, that this equaled 0 if the absolute value of r is less than 1. If this is a fraction, and it diverges otherwise. A really good rule to have for just everything that we're going to be doing for the rest of the semester, of which there's very little left. So let me explain this, because this might look weird to you just seeing it in this abstract form. What I'm saying is that if I have something like a third and I raise it to the nth power, think of what you're doing. Every time you raise it to a higher power, you're taking a third of what you had before. So this is a third of a third of a third. So that thing shrinks down to 0. So this goes to 0 as n goes to infinity. A third of a third of a third of a third of a third keeps shrinking. If I had something like this, negative 1/3 to the n, that's gonna kind of bounce. So let's think about what that might look like. So when n equals 1, we've got negative 1/3. When n equals 2, we got a 9th. When n equals 3, I got negative 1/27th, and then I got a positive 1/81st. So this, when it's negative, I've got something that goes like this. But it dies to 0. It just alternates sign, S-I-G-N, each time. So that's a loose justification for this result right here. But that result is going to help us answer this question. we're going to assume that the absolute value of r is less than 1. So it's a fraction. It's a number between 1 and -1. Actually, let me write that out. This is what I'm saying. Because sometimes folks have trouble thinking about absolute values. It's just a number between -1 and 1, not including those two numbers. So where does this go as n goes to infinity with that assumption? What does the right side look like? Part of it goes to 0. This goes to 0, right? You see that? That part goes to 0. Everything else is fixed because it doesn't even have n in it. So what does this become over here? Quite lovely, yes. Look at that. That is how you add up an infinite geometric series. This is, so with this assumption here, this is equal to the first term over 1 minus the common ratio. That's a beautiful way to think of it. First term over 1 minus common ratio, and you're good to go. Hey, Zeno. Guess what? If we have infinite amount of time, we're going to get there. Let's show that. So here's my infinite geometric series. Let's add this up. Let's use the a over 1 minus r formula. What's a? 1/2, beautiful. What's the common ratio, r? 1/2. Does everybody see that? It's a half. Just look between terms and see what you multiply by to get to the next one. If it's not a common ratio, we're screwed. So for everything in the web work, it will be. Everything will be. And we can only, we check, we need a little check here. Just always check, is r between -1 and 1? Because if it's not, you just say divergent. The series will just blow up. It does not come to a finite value. But we're good to go. We're half, 3/4 of the way between here and here. It's all good. So our sum is equal to our first term over 1 minus our common ratio. How far did we travel? 1 unit. So those add up. That sum adds up to 1. In your face, Zena.
So you can try.
You can travel. Yes, luckily. You will be able to leave class today. We can travel, given infinite amount of time. So this is what we're going to play with for a little while. Let's do some stuff. Let's do a fun, a fancy Zeno. Let's fancify Zeno's thought experiment. So here's a new experiment. Me and the door, that's 1 unit. From here to there. My new game, instead of moving forward a half, is to alternate. Traveling forward half the distance and traveling backwards half that distance, remaining distance. So I'm going to walk forward a half. And then I'm going to bounce back a 1/4. So half the remaining distance. Then I'm going to bounce forward 1/8. Then I'm going to bounce backward a 16, 32nd. I end up doing this little shuffle, right? It's like, this is like great. This is like you go to a dead show. This is what like everybody's doing.
It's true.
It's just this. There's twirlers too. Lots of twirlers. So that's enough of seeing me do that. Let's figure out this experiment. So what happened? I moved forward a half. I moved backwards a 1/4. I moved forward 1/8. I moved backwards a 16th. I went forward a 32nd, backwards a 64th, and so forth and etc. Put a plus minus there to indicate the alternation. When you use plus or minus, the sign on top is the sign of the next thing. So had I stopped here, I would say minus plus to indicate what's happening. So the thing on top is the sign of the next thing. Now let's go ahead and do that, just to do something weird there. That's just convention. So, the sum, first off, what's our common ratio? Maybe we should even just check with that. What's the common ratio? And yet, what did I multiply by to get from here to here? Negative a half. And then notice from here to here, it's another negative a half. So each time I'm multiplying by negative half, it's giving me a sign flip, but also a decrease by a half of the magnitude. So r is negative a half. We do our little check. R is less than 1 in absolute value. Awesome. Proceed. Otherwise, you could get some real bunk if you don't assume that. So we got this. What's my first term? Half. So our sum is equal to first term over 1 minus, be careful here, it's 1 minus a negative number. So it's 1/2 over 3/2. What does that simplify to? 1/3. Thank you. Yay. Thank you for doing the fractions. You did great. Just remember, you can always turn a division of fractions into a multiplication. You just take, this is 1/2 times the reciprocal of the bottom. Right, so if that feels better on your mind, and it might, do that. You can also multiply it top and bottom by 2 to clear out the fractions. Either way, 1/3. So what that means is that, let's look at this as a number line. So if I start at a half, or move forward a half, and then go back a quarter, so this is where I'm at the second step, and then move forward an eighth. So that's 3/8 right there. And then go backward a 16th. I'm not gonna keep doing that. But then I'm back here, and then I move forward here, and then backwards here, and keep doing that by half. That means that I'm honing in on a third. That if I kept doing this forever, it's the same thing as just walking forward a third of the distance. Which I think is kind of neat, kind of surprising, right?
That'd be the limit?
Uh-huh. Yep. Indeed it would. It's next in my little sheet of fun. Oh, here's a cool example. So let's tie this to things you do all the time, but you didn't know infinity was really lurking in this interesting way. So here's an application. It's a very nerdy, mathy application, but still an application. More of like a, oh, aha moment. So repeating fractions. Repeating decimals, excuse me. Let's just use that term. So if I had the decimal 0.135, 135, 135, and then that goes on and on forever. Sometimes we write that like this. Probably seen that notation. We put a little bar over the repeating part. This is an infinite geometric series. Just a very fancy one. So let's think about this as view as an infinite geometric series. So this is actually 135 over 1,000, that's this part, plus 135 over 1,000 squared, 1,000,000. Oh wait, am I doing this right? Let's see. Yeah, because divided by 1,000 is okay. That's all good. 1,000 squared plus 135 over 1,000 cubed, and so on. You can check me out on that. This is 1,000,000 down here, so like just really quick, divide this by 1,000,000, shifts the decimal 6 places to the left, because that's the number, well, that's the power there. That's the number of zeros, so 1, 2, 3, 4, 5, 6. So this number here is 0.00135. This one is 0.135. just to help make this a little bit more sensible. And then this one's got 6 zeros in front of it, and then 1, 3, 5. And when you put them all together, this plunks right into there, lovely, and then this piece will plunk right into there in a perfect way. So we have an infinite geometric series. How cool. So what our first term, A, is 135 over 1,000. What is my common ratio? 1 over 1,000, yep. To get from here to here, you just multiply by 1 over 1,000, right? Because the top's not changing, just the denominator is getting an extra 1,000 on it. So R is 1 over 1,000. We're done. R is less than 1 in magnitude. Check. So our sum, so this number up here, 0.135 repeating, can actually be written as the first term over 1 minus the common ratio. So already, we're close, but we don't like these complex fractions with fractions within fractions. That's amateur hours. We don't do that here. We're gonna make this a nice simple fraction. I can multiply the top and bottom by 1,000. So I'm gonna multiply the top by 1,000, and I get 135. I'm gonna multiply the bottom by 1,000, and I get 1,000 minus 1. Boom. This is 135 over 999. So if you type this into your calculator, you'll get that, which is kind of cool. Let me give you one to try. Oh, by the way, could this be simplified? Yeah, it could. What could I pull out, like a 9? How do we know the top is divisible by 9?
It's all up here.
What?
It's all up here.
Oh, damn. You can't even like communicate it,
No.
because it's just too much.
You gotta,
Well, let me translate. The sum of the digits are 9 on the top number, so it's divisible by 9. That's the way to tell. So this is divisible by 9, this is divisible by 9. When you divide that top by 9, you get, what, 9 and then 4, 5, 15. So this is 15 over 1, 1, 1. Can I simplify more? What's the top divisible by?
3.
3. And what's the bottom divisible by? 3. Sum of the digits is a multiple of 3. 6 and 3. So this doesn't look like it should be divisible by stuff, but when I divide the top by 3, oh, now we're good. And then the bottom divisible by 3 should, I don't know.
37.
37, thank you, how cool. There we go. Type that into your calculator and smoke it. You'll get that out. Kind of cool. I think it's kind of cool. All right, so that's a neat application. My God, what was I thinking with this one? Good God. Oh, yeah, here, can you please find this sum, if possible? If not, tell me it's divergent. What does that add up to? I think now we're going to do some of the wet worky kind of problems together. So you have an example of each, especially the weirder ones. What's the common ratio?
-3
-3 halves. So the first thing to look for is that common ratio. Should I bother going forward? Nope, doesn't converge, because this is bigger than 1. So here's the first thing to check. So step 1 is, eventually step 1 is going to be identifying a kind of series we have. That's gonna start on Friday. We're gonna have more than this kind. We're starting here because it's chill and totally ownable. But step 1 is find the common ratio and check, is absolute value of R less than 1? If not, divergent. So let's put that into the algorithm. If not, divergent is your answer. And you would give this reason. One of the things you're gonna have to get used to is giving these reasons. So I would say that, first off, I would say here we have a geometric series. We don't have to write much, with R equals -3 halves. Since absolute value of R is bigger than 1, it diverges. So it's kind of a little bit of, it's not even a sentence, it's just a bunch of words, but it could be put into a nice sentence if we wanted to take the time to do that. Let's do a couple more.
Dr. T,
Yes?
how do you get how you found R?
Cool. So what do I multiply by to get from here to here? So look at the top. What did you need to multiply across the top?
3.
3, and then what about the bottom? And then there's the sign change, so -3/2.
So if there's a sign change, it's always negative? Okay.
Yes, good rule of thumb. If this thing alternates, R is negative.
Okay.
Yeah, does that make sense? Cool. Alrighty. How about this one? So now I'm gonna use summation notation. Let's just talk about that really quick. So this thing here can be written in sigma notation, which we saw a long time back. So this means sum. Gonna add up stuff, sigma, Greek S, integral stuff, you know. No integrals here though. We just have A times R to the nth power. What does n start at here? At 0. It's 0. So this is, because the n is on the R. So there's like a secret R to the 0 here and then R to the first. Does that make sense? Yeah? Good? Okay. So this is n equals 0 to infinity. Okay, well, no, we'll come back to that. So let's just look at this one together. Find, if possible, sum of k equals 2. I'm just using a k here to, you know, put v on rows, so forth. So 3 to the k plus 1, or 4 to the k minus 2. Oh shit. That looks complicated. But you know what? It all comes down to knowing the common ratio. That's it. And getting a constant as my first term. So notice here that this first term is constant. You want to get that before you can use that formula. You have to have a first term. So constant first term to use the formula. If you don't, you just have to do a little tweaking. And so that's what this problem's all about. What I would do here is start to write this thing out. Well, there's a couple of ways to do this. Let's look at all of them. So one way to do this is just start writing out what does it look like. And I think that's always a good idea. When you get these sums that are like this, your brain isn't quite acclimated yet to doing stuff with them. So write it out, get a sense of what you have. So when k equals 2, the top is 3 to the third. And the bottom is 4 to the 0. So this is k equals 2 right here. Plus, then k goes to 1. Plus, so now we're going to do the k equals 1. The top is 3 to the 4th, because then yes, k equals 3, excuse me. When k equals 3, that's the next thing here. We've got 4 to the 1st.
How's it k to the 4?
So look at where k starts. So k runs from 2 to 3 to 4. Look at the starting index
It's
here.
because you said k equals.
Did I? Oh, did I?
Yeah.
Oh, okay, I didn't mean that.
So you mean k equals 3?
K equals 3,
Oh.
and then the exponent becomes 4. Yes, that's what I meant. Thanks for correcting that. Does that make more sense? Awesome, okay. So this is k equals 3, thank you. So when k equals 3, it's 3 to the 4th over 4 to the 1st. And from here, once you get the rhythm, you don't even need the original formula anymore. You just see that these powers are bumping up each time. So, we have a constant first term. There's going to be a time when we don't, but right now we do. This is a constant. I can use that formula. I'm good to go. So what's my first term? This.
27
Oh, you're looking for the R? Yeah, you're jumping in.
sorry.
Yeah, that's cool. No, that's great. So yeah. So what is it? 3, you were right, because that gets you there. And then, did you say 3/4?
No, I did not, but I'll pretend I did.
Do you see that though, Olivia?
Yeah.
So there, that's times 3, and then there, that's just times a 4. And that gets you every other term here. 3/4, we're good to go. This is 27, right? That's just 27 over 1. Crumpling here. So the sum is equal to the first term over 1 minus the common ratio. And we're good to go. 27 over a quarter. That's 4 times 27, which is like 108. Does that sound right? What's 4 times 27? Is 4 times 27 108? Yeah. So like, look, this is just 27, multiply top and bottom by 4. And you get 108. Shockingly whole, given that craziness up there, like shockingly, like just an integer. Quite lovely. Questions on this? Yeah.
May I ask why it's a whole number, or do we just not know?
I mean, it just is. It just worked like it's like a rigged problem to be a whole number. So this doesn't represent any physical phenomena, so I can't like give you a like, it's because the mass of the electron is this or anything like that, you know. It's just rigged to be perfect. We could easily make it not a whole number by making that our first term, and then that number on top would not be, well, maybe, I don't know. This might be unriggable, or perfectly riggable all the time, yeah. It's just mathy bullshit. Not representing real life. Let's do one more. If there's no more questions on that. Yeah, okay, cool. So we'll do this, and then I'll give you some time to find, well, actually, let's do 2 more. Sorry. So now I showed you how to do that. Can you please find this? Sum from n equals 3 to n. Now you're going to have to use the finite formula here. So sum equals 3 to n, negative 1/4 to the n. So let's write out what that is, but you still want to use this formula. S sub n equals a times 1 minus your common ratio. This is your first term. And then down here, you're gonna have 1 minus r to the n. Here, the n is the number of terms. That's a great way to just think of that. So the exponent there, that n, is how many things I'm adding up. So can you just kind of like contemplate that? Maybe writing it out will help. I wouldn't like work out all the powers of a fourth. That would be not helpful. But writing it out as this. You help. I mean, it's totally write-outable, right? So. You don't have to worry about convergence when it's a finite sum. I'm going to make that little note here. It's only when we go to infinity that that's a problem. No? Yeah, question. Yeah, please ask.
Isn't the R to the N
I'm sorry, ask that again.
So
Oh, did I? Oh,
The
shit,
N.
yes, thank you, God, yeah, thanks, sorry, everybody, yes.
Hmm?
I had the N and I put the N in the wrong damn place. Thank you. Yes, good call. Thank you. I'm super grateful for your furrowed brow. Thank you. We just really need to use the right formula and identify all this.
7? For N?
Mm-hmm. 1, 2, 5, 6, 7.
Number of terms.
It gets tricky. It's yeah. You think you can just subtract, but then you got to add 1 to it. Yeah, yeah. So that's negative 64th. And this might end up being like painful. I don't know if we want to raise a fourth to the 7th. So if you can just write it out, you could get a calculator and do it, or let a computer do it. That 1/4 to the 7th, I don't know about that. I guess it's not too bad. It's 64 squared times an extra quarter. Does anybody have a calculator that could do that for us, or a computer? You could just
The
go.
whole thing?
Just actually, first off, just this piece.
16,384.
60. Okay.
That's the fourth.
Okay. So 6. So it's 1 over, and it's going to be negative, right? So this will become a plus. So that's not a negative to an odd power. That makes it a negative result. That becomes a plus. And then what was that number?
16,384.
That sounds totally right. It does, like I'm not even joking. And then the bottom's just 5/4. And then, God, I don't know. You know, Yes, oh,
Why is R equals
negative fourth.
no, why is R equal to?
So what is it, so look at the first term, it's that negative 1/4 cubed. What do you have to multiply to get to the next term? Well, this is, I see why you're saying that, but this is negative a quarter, negative a quarter, negative a quarter. And then this one, if there was a minus out in front, I would agree with you. But this is actually 4 negative a quarters multiplied together.
Oh,
Does that make sense? Yeah, that's a good question. Yeah, had it been this, like this, Vivian, I would totally agree with that. Yes. Good stuff to talk about. And then this is, I don't know, did anybody got a number for me? Nah. Nah. It's a lot. Did you work it out, Cassie? Okay. Well, shit, I'm gonna do it. This is, let's see, I'm gonna multiply top and bottom by 64. Clear that out, so I get -1, and then this will just stay the same because I've already multiplied the top by that, so 16384. And then the bottom times 64 is going to be just 80. 16 divided by 4, or 64 divided by 4 is 16, times 5 is 80. And then one more step, or so. This is gonna be negative 16,385 over 16,384, and then divided by 80. Oh God, I don't know. I don't care anymore. It doesn't matter. It's equal to some number, some negative number. Let's be more precise. Yay! And we could get that to any precision we'd like. Did anyone actually crank it out to any precision? Did you? No?
I said like -0.01, but I don't know if it got put in the calculator properly. 'Cause it was
Okay,
so
well,
big.
we'll just leave it here.
I got that too.
Negative 0.01-ish.
Yeah, I left it in a fraction.
Yeah, that's, oh, you left it as a fraction.
Yeah.
What'd you get?
Negative 3,277 over 262,144.
Cool.
That's too many.
Good work.
She did that all up here.
I believe it. Could you actually, yeah, could you crank this one out, Cassie, just for me real quick, please?
That one.
Just this to see.
That looks right, yeah.
Yeah?
Yeah, it looks like the same number I got earlier.
Cool, awesome. Are you explaining the fraction work?
No,
Oh, what's,
you
yeah,
might
what's
have
up?
said this, but I'm like, I don't know.
It's okay.
So the R, even though it's -1/4, it's technically like,
What's,
right,
it's not a question yet.
right. Oh, it just can't be bigger than 1.
It can be, so when we have a finite sum, it doesn't matter what
Oh,
R is.
okay.
Thank you.
You're welcome, absolutely. So like, for example, just really quick example, I could have R equal like 2. So I could do this really quick. First term is 1, so A equals 1. What's R here? 2. And how many terms do I have? 11, because this is 2 to the first, right? So there's the 10 plus that extra one, so 11. Yeah. So this sum is going to equal first term, or A, yeah, times 1 minus 2 to the 12th. Oh wait, was it, oh, it's just R to the end. Okay, so 11, yep. Over 1 minus 2, and then whatever that is. I don't know what that is. We could find it though. Okay, I got one last one for you. This one's a little more open, but it's certainly something that might appear in a web work. So we have n equals 0 to infinity, infinite sum. So I've got restrictions on R. On top, I've got x minus 3 to the nth over 5 squared. So the problem here is find all values of x that make this converge. Okay, so let's talk about that. So find, there's two parts. One, find all x for which this converges. And then part two is going to be, what does it converge to for those? And I'll just say when x is proper, meaning it falls in that range we got for the first one. This is kind of leading into one of the last things we'll do in our class together. This is called a power series. And what that means is it's an infinite series that depends on a variable. Yeah, you do need a parenthesis. So this value will change depending on what x is. I'll get a different sum out, because I'm actually changing the things that I'm adding. So let's answer part one first. So part one, we need, so what is R here actually? What is R? What is changing? Let's write it out a little bit. We'll write out the first couple terms. First term, n equals 0. So I've got x minus 3 to the 0 over 5 squared. Next term, I've got x minus 3 to the first over 5 squared. Then x minus 3 squared over 5 squared. What does R equal?
X minus 3 divided by 5.
Is the bottom moving though? Did I multiply by an
Oh,
extra
still
5?
two. So over 1.
Just over 1. Yep, just x minus 3. Perfect. So R is just equal to x minus 3. I'll come back over here where I started. So R equals just x minus 3. It's that number. That's some number. We don't know what it is. But we do know that we need the absolute value of R to be less than 1. In other words, between 1 and negative 1. Have to be in this range. So now I'm going to replace this and I get an inequality. So we need absolute value of x minus 3 to be less than 1. And as long as that happens, that sum is finite and converges. So, i.e., I need, and I highly recommend thinking like this. This translation here is going to make life so much easier for you. So we have this. How do I isolate x in the middle of that so I know something about x in this as opposed to x minus 3?
Add 3 to both sides.
Add 3. Add 3 all the way through. So add 3 to everything. And you're going to get 2 less than x less than 4. Now I've got my range of x values. So as long as x is between 2 and 4, that sum adds up to something. So these are the valid x values. You could almost think of it as the domain of that thing, because this is actually a function. It depends on x. You put in an x, you get out a value. This is the domain of that function, is a nice way to think of it, using like ancient terminology for you, for all of us. So what does it converge to when x is between 2 and 4? Now we just go to the formula. So for part 2, I've got this, I don't know, 1A, 1B, 1C. Part 2 is what does it converge to? When x is between 2 and 4, x minus 3 is less than 1 in magnitude, the sum is equal to first value over 1 minus the common ratio. We already identified the common ratio, Cassie gave us that. We needed that for part 1. So this is equal to the first term. What's my first term?
What do you plug in 2 for x? No, 1.
Close.
What?
Don't forget, the top is 1, but what's the bottom? What is this? 1 over 25. So this 25, don't forget about that part. We hadn't used it for the analysis. Does that make sense? It's kind of, so you just gotta be careful. So A equals 1/25. And R is x minus 3. Better use parentheses. Let's simplify. So this is 1/25 over 4 minus x. See how I got that? Because that's 1 minus x plus 3. I've distributed the minus. And so this is our function that represents that sum. And that sum from n equals 0 to infinity of x minus 3 to the nth over 5 squared is that function right there. So you've taken this infinite thing and turned it into something really finite. Remember that our domain was this. That's really good. It keeps x away from 4, which is a super bad number for this denominator. We don't want x to equal 4, and it doesn't. It's nice and safe. Hell, we could even graph this thing out if we wanted. I know you don't want, but I do. So if you graph this out, let's see, when x approaches 4, it blows up. So when x gets closer to 4 from the left side, this goes to infinity. So we've got some asymptotic action there. And then when x approaches 2, this approaches, so as x approaches 2, 1/25 over 4 minus x approaches, you can just plug and chug on this one. So 1/50. So if this is 2, and let's just say that's 1/50. Here's the graph of all the possible outputs for that sum. Looks like that. As x gets closer to 4, this thing blows up. What does that look like when x equals 4? Let's just think about this for a minute. So when x equals 4, so if x could equal 4, what does that sum look like? What's the top? What's 4 minus 3? 1. What's 1 to any power? 1. So the top is always 1, and the bottom's 5 squared. So what you're doing here is just adding 1/25 forever. You can bet that's going to pile up to infinity. When we're adding stuff up, and I want to kind of use this as just a little pivot to something that's coming up. When you are adding up infinitely many things, so just think about this. You've got a pile of sand that you're dropping, or a pile of stackable discs. So I've got this little pile of stackable discs, and I dropped the first one. Do I want stackable discs? Sure. You want the size of the things you're stacking up to die out. So the next one, I'm going to make it a little bit smaller. That doesn't look at all smaller. I'm going to make, this looks stupid. This is stupid. If I'm adding up infinitely many lengths, so I'm going to take that and I'm going to add another thing to it. I want these things to die out, because I would like it to stop progressing at some point. So when you have an infinite sum, you need the terms to die to 0 to have any hope of this thing stopping accumulation. And I don't know if you remember this, I feel like we talked about it. They have to die to 0 fast enough. Have we talked about that in here? I feel like it was a long time ago. they have to die to zero fast enough. Oh yeah, because we had like, when we were looking at this. When we looked at this, we needed this exponent to be large enough so that these things died off fast enough so that this area was finite. The same stuff is happening here. You're gonna see so many parallels between this, honestly, and all the stuff we're doing. That's all I got to tell you. So, you got some homework to do. We have 10 minutes. You look shocked. We have 10 minutes, not to do the whole assignment. Do you want to start? I'll tell you what, you want to leave, leave. You want to start on it, start on it. Yes, Kelsey.
Can we go over number 2?
Can we go over number 2?
Yes.
What is, all right, hold on.
I'm just kind of confused by this.
Okay, yeah, let's clarify that. Yes, ma'am, absolutely.
What?
Yeah,
So Cassie's been working over there.
I only did the first one.
It's okay. What can I see number 2, please?
Yeah, it's just like about warfarin.
Your shoelaces are so cool. Oh.
Yeah, it just looks kind of complicated. I'm
Oh,
sure it's
okay.
not that hard once we still figure it out, but
Yeah, how do you say that word?
warfarin,
Warfarin?
it's an anticoagulant.
Oh,
Blood
cool.
thinner.
Awesome. So there's an actual application problem here. So what I would suggest here is kind of following the pattern. You can almost just look at the sums and forget about the rest of it. So we've got Q of 1 is this number, and then it's got milligrams on it. And then Q of 2 is 7 times 7 100ths times 1 plus 7 100ths, yeah, milligrams. And then Q3 is 7 times 7 100ths times 1 plus 1 over 700 plus 1 over 700 squared, blah, blah, blah. I wonder if they want, I think you could just literally enter the next formulas, but that sounds painful. So here's what I would recommend to do on that one.
And it's 7 over 100 for the.
Oh,
Oh no.
did I get it right?
Yeah, 7 over 100 for the following, not 1 over 700.
Oh, 7 over 100, thank you. Oh, yes, thank you. Okay. Okay, so here's how I would do this problem. I would get out my calculator and crank out this value. And then think about what you're adding each time. Because like they ask you this huge slew of things like, what is Q of 10? What is Q of 11? So I would get my calculator out and figure out the last thing that they gave me. And then notice what you're adding each time. So what are you adding for the next one? Look here, you've got 49 100ths, right? Times the next thing that, and this is this, right? This is actually this. So to move from here, if I knew this sum, just notice that you're adding 49 100ths times 7 100ths squared. So just take this sum, you gotta find one somewhere. But then add this, the thing that you're adding each time. To get from here to the next one, I would add 49 100ths plus times 7 100ths cubed. And then just get my calculator out and add that and type that answer in. So that's how I would do all this. And then when you get to the limit part, I think they ask, what is the limit as n goes to infinity of q of n? It's a geometric sum. So find first term, common ratio. Common ratio is pretty easy, just 7 100ths. Right here, so equals first term. You'll have to figure out what that is. It's literally that. So first term, 49 100ths over 1 minus common ratio. I'll leave that part, which I think you can see it like on the board. Does that sound good? Cool.
That makes sense. I think the 1 is confusing.
Yeah, I can see that. Alrighty. Alright, leave. Leave. I'll stay here for 5 more minutes. Bye, everybody.
There's fun stuff happening on the floor.
Is there fun stuff happening?
Yes, it's that week, so we're doing a lot of, we're doing obstacle course and push-ups.
Oh, cool. Oh, nice. That's where everybody heading to the court. You're heading out to the obstacle. Yeah, absolutely. Absolutely exciting. Awesome. Yes, it sounds like it. Sounds fun.
Give me so. Awesome. Gave me so many questions.
That's cool. Sounds good. Hopefully it didn't give anyone anxiety. Yay!